So the next talk is a distinguished POPL paper. It is a talk about probabilistic concurrent reasoning in outcome logic, independence, conditioning invariants, and it will be presented by Noam Zilberstein. Thank you.
Great, thank you for the introduction. So the goals of this paper were to come up with expressive reasoning techniques for the combination of concurrency, randomization, by which I mean like discrete probability, and unbounded looping. And the applications are, there are a lot of applications in both security and also randomized distributed algorithms. For a long time, randomization has been used to do things in distributed systems that are either difficult or impossible to do deterministically. So we had a lot of ingredients to work with. The first one is concurrent separation logic, which is kind of the gold standard for compositional reasoning about concurrency. The second one is probabilistic separation logic, which is a slightly newer idea, but it's another compositional technique for reasoning about probabilistic computations. And the third one is outcome logic. So the basic idea of what we're doing in this paper is just putting these three things together, although it's much easier said than done. Okay, so let's start with concurrent separation logic. The kind of core piece, the core thing that concurrent separation logic gives you is this parallel composition rule, which says that if you can separate the program resources so that each thread is operating on its own portion of memory, then you can analyze the two threads compositionally and you don't have to worry about all the different ways that they can be interleaved. Okay, so let's think about how might we want to use this in a parallel program. Well, the most basic, randomized parallel program you might think of is just to flip two coins in parallel. And when we do that, we can look at each thread individually and say that in each thread, the outcomes are going to be uniformly distributed. They'll be distributed like fair coin flips. So we have some notation here. This P with the ceiling brackets just means that P occurs with probability 1, and this O plus modality allows you to bind a new logical variable that's distributed according to some distribution. And so now if we were to use the PAR rule that we saw on the previous slide to put these two specifications together, we might get something where we basically join the post conditions and preconditions with a separating conjunction. But the question is, what does this actually mean? So if we take an interpretation based on probabilistic separation logic, then the separating conjunction is not only going to mean that the state is disjoint, but also that we get some probabilistic independence guarantees. And the really nice thing about doing that is that we actually get the full joint distribution over all the program variables. So not only do we know that X is 0 with probability 1/2 and Y is 0 with probability 1/2, but we can multiply the probabilities to get the probability that both are 0, which is 1/4. So this is a nice start, but of course, the difficult and interesting part of reasoning about concurrency comes with shared state. And concurrent separation logic gives us the ability to reason about shared state using resource invariants. So, we add this component I to our judgment. I is an invariant, which basically means that it's true at every step of computation. And so as long as the two threads obey this contract, they can interact with shared state. And then we have additional rules to reason about shared state. So you can allocate an invariant by basically saying, if I is true at every step of the program, then it must be true before and after the program executes. You can also use an invariant. You can open an invariant because if I is true before and after the program executes, and the program is just one atomic instruction, then I is an invariant of that program. So, these are the rules of concurrent separation logic. I haven't yet said if these are valid in our model. The first step of the paper was to basically make these rules valid in our model. But the probabilistic setting is much more complicated than the non-probabilistic setting, because you don't just have to worry about, the fact that state can't be messed up by the scheduling, you have to make sure that the independence also holds. And there are a lot of ways that the independence cannot hold, right? So you can get implicit correlations that are introduced by the scheduler. Here we have an example where in the left thread, X is distributed like a coin flip, but the parameter of the coin is coming from shared state. So the scheduler can, choose an interleaving where the parameter of the coin flip on the left side is dependent on Y, which is some state of the other side. So we get some correlation, and these things are not independent. So the question is, how can we have this parallel composition rule that's sound in this setting? And the solution we came up with is to use precise assertions. So if you're familiar with separation logic, the notion of precision here is exactly the same as in other separation logics. We say that an assertion is precise if and only if it has a unique smallest model. If that doesn't mean anything to you, don't worry, you can completely forget about it. The intuition of precision is that an assertion is precise if every measurable event has an exact probability. So examples of things that are precise are P in the ceiling brackets. Here, P is the measurable event, and it has probability 1, so it's precise. Saying that something is distributed like a biased coin is precise because we know exactly how likely each outcome is. And then you can join two precise assertions with a separating conjunction, and you also get something precise. But an example of something that's not precise is a coin flip where the parameter is bounded, because now we don't know the exact probabilities of each outcome. We only have a bound on the probabilities. And the par rule now has this additional constraint that the post-condition of both threads must be precise. And what that essentially does is it says that you can't measure the non-deterministic behavior of the scheduler. And because it's not measurable, we get independence of all the events that you can measure. So to go back to the previous example, if in the first thread we replace this assertion about X being distributed like a coin flip with a bounded parameter with something that's just true with probability 1, now we have two precise assertions that we can put together, and the par rule applies. So what's going on here is that the exact value of X is not measurable. We can only measure, some probability 1 event relating to X. And so we get independence of all the events here. Okay, so the first part of this paper is, we took the rules of concurrent separation logic, we reinterpreted them in a model based on probabilistic separation logic. This was a lot harder than it may look, but we got these to work. So the next component is what additional rules do we need to actually make this logic usable? And from that, we turn to outcome logic. So outcome logic gives us rules that allow us to do case analysis on the outcome of random sampling events. Here we have we have a specification where in the precondition we're stating that the initial states are already randomly distributed. We can then reason about this pointwise, basically, for every value of X, and then put the result back under this outcome modality. So let's look at another example of how all these rules come together. Here we have a program where first we flip a coin, and then we read from that coin flip into parallel threads. The issue here is that clearly Y and Z are not going to be independent, because both of them are derived directly from a shared source of randomness. So the question is, how can we actually use the par rule to reason about this program, given that there's a clear correlation? Well, let's look at the derivation. So the first thing we're going to do is split up the sequential composition. And for the first component, it's obvious that we can just say that X is distributed like a coin flip. And now we can move on to the second component. So for the second component, the next thing we're going to do is use this outcome splitting rule to reason underneath the O+ modality. And now we're in a position where X is deterministic. It's universally quantified, but it's deterministic. The next thing we can do is move the information about X into the invariant. so that we can share it between the two threads. Then we can use the parallel composition rule. And finally, we're in a position where each thread is just one atomic instruction, so we can open the invariant, and we see that in the first thread, y points to x, and in the second thread, z points to not x. So all we have to do is bubble all that information back down. And what we end up with is some sort of conditional independence assertion. So y and z are independent, conditioned on the outcome of this coin flip. And this idea sort of comes from, prior probabilistic separation logics like Lilac and Bluebell, but we really need to use this case analysis rule, which was not valid in any of the prior probabilistic separation logics. So this outcome reasoning ended up being really critical here because there are a lot of different forms of compositionality, so you have to be very careful about the order in which you apply these rules. Okay, so we started with these rules at the intersection of concurrent and probabilistic separation logic. We added outcome logic, and now we have this expressive set of rules that you can use to reason about a lot of different types of programs. I want to now talk a little bit more about the meta theory behind this. So the semantics for the underlying program language here is based on a model called POM sets with formulae, which we published in Concur last year. I'm not going to get into exactly how this model works because it's very complicated, but what it gives you is this linearization model where you're basically able to take these parallel probabilistic programs and interpret them as maps from states to sets of distributions of states, where the set is the set of non-deterministic scheduler behaviors, and then for every behavior that the scheduler could have, you get a distribution of all the random behaviors that can occur. Now, like I said, the exact definition of this model is very, very complicated, but it gives us some very nice properties. So yeah, I'm not gonna go through all of these line by line, but if you glance at this, this looks a lot like the standard semantics of any kind of monadic programming language that you might expect. So the takeaway is that we had this other paper on demonic outcome logic, which was a logic for non-determinism plus probability, and essentially most of the meta theory carries over from that logic to probabilistic concurrent outcome logic because we have these nice compositional properties. But of course, you don't see any nice compositional properties here for concurrent commands because you don't get any. When you compose two threads in parallel, you can completely change their behavior. So we needed to develop completely new theory for that. And just to give you a taste, maybe I can entice you to read the paper. There were a lot of challenges. So the first one I already alluded to, we needed to tweak the measure theoretic model that we use for assertions to enable the type of case analysis that we needed to do. We had two sort of key theorems that motivated the soundness of our inference rules. The first one is invariant monotonicity. So that says that if you add an invariant, you can only increase the set of random behaviors that you're going to see. And then the soundness of the parallel composition rule essentially required us to show that the probability of any composition of two events in a parallel program is equal to the product of the probabilities of those events just by evaluating the threads on their own. There's some other issues, so we had to introduce this idea of weak frame preservation because certain types of case analysis on non-deterministic state break all the independence guarantees that you might want. We had to contend with that, but then we also have simple rules to get the frame rule back. And then our logic also supports reasoning about unbounded looping and almost sure termination. So this is the first probabilistic separation logic that has unbounded loops. So I will finish just by showing two examples from the paper. The first one is a concurrent shuffling algorithm. So this is based on a result from Bakker et al. 2015. They showed that using a divide and conquer style algorithm, you could get up to 7 times speed up for shuffling over just doing it like the standard Fisher-Yates. So here we have an algorithm inspired by that, where we randomly partition a list into 2 segments. We shuffle each segment in parallel using Fisher-Yates, and then we concatenate the results. And we can show in our logic that the result is a uniform permutation of the original list. The one thing I want to call out here is that the independence guarantee is crucial, because if we were only able to show that L1 and L2 were uniform permutations, but they're not independent uniform permutations, we would not be able to complete the proof. So the independence is really important. Okay, we also have this von Neumann trick program. So this is a protocol for simulating a fair coin given a biased coin. But it's kind of a tweaked version where the bias of the coin is stored in shared memory, and it can be altered by some adversary in another thread. So we were able to show that after this program terminates, the distribution of outcomes X is distributed like a fair coin. This specification also implies that the program almost surely terminates. So we have a unbounded loop here, but the loop terminates with probability 1. And the other very interesting thing about our logic as a whole is that this specification also guarantees that if you compose another thread in parallel that's altering the probability P, it can't introduce any correlation with X. So X is going to be independent of whatever local state the other thread has. So that's very interesting as well. Okay, so to sum up, I introduced probabilistic concurrent outcome logic. It's an expressive logic for reasoning about the way that outcomes are distributed in parallel probabilistic programs. We use separation logic to compositionally reason about concurrency, but the meta theory was kind of brand new and quite a bit more complicated. For future work, we're interested in looking at different scheduler assumptions. So we used a very strong notion of scheduler. We're interested in ways that we can relax that strength to reason about different types of programs using things like fairness and oblivious schedulers, where the scheduler cannot see the outcomes of coin flips. We are also interested in incorporating iris-style resources so that we can, reason about shared state in more expressive ways. And since we submitted this paper, we've actually already started formalizing some of the key theorems in Lean. So we're hoping to finish that effort. And with that, I'm happy to take questions.
A question? Yeah, thank you for the very nice talk. So, as you mentioned, some of the other probabilistic separation logics only have rules for bounded loops. Do you think your insight can be backported to those logics, or is it a fact of the abstraction model of outcome logic that has no direct translation?
So you're talking about the ones where they interpret separation as independence?
Yes.
Yeah, I think it can. I'm actually not 100% sure what the blockers were in all those cases. The theory is a bit more complicated, but I think it could be, yeah.
Hi, thanks for the talk. So you mentioned this restriction on the, if I understood correctly, the parallel composition rule that the post condition has to be precise, which sounds like it could be annoying or in the way or restrictive. So do you have some experience how this pans out in actual examples in terms of, does it prevent you from proving things you want to prove? Are there tricks you can use to get around this or something like that?
So it didn't prevent us from proving anything we wanted to prove. So I mentioned that we have this weaker type of separation that doesn't imply independence. We didn't end up developing a parallel composition rule using that, but I think you could, and then you could relax the precise thing. One thing I will say, though, is that precise. I mean, although the definition is very similar to standard separation logic, the meaning is a little bit different because kind of the granularity which you're talking about resources and stuff. So it's not really constraining anything that you could say as like a standard separation logic assertion. It's really, sorry, I couldn't hear.
Exists is not precise, I assume, on anti-disjunction.
Yeah, those aren't precise, but if you put exists inside of these brackets that say with probability 1 there exists, then that is precise. So hopefully that helps a little bit.
Other questions?
Hi, great talk. Appreciate it very much. Can you spell out the validity condition that you get for the triples? Or at least for some of the examples that you...
Yeah, sure. So I mean, we're based on, this is kind of the semantic model. You have a function from states to sets of distribution of states. The triples are demonic in some sense, in that the postcondition applies to every possible scheduler behavior. So when you have a triple, it's quite complicated because you have distributions which are what you're computing over, or that's what the semantics is over. You have probability spaces which are modeling the pre and post condition, and then you also have the frame preservation property. So if you look at the actual definition, it's quite complicated, but essentially what it's saying is if you take a distribution which satisfies the precondition and you run the program using this model, then any distribution that results, basically for all distributions in this set of results, that distribution satisfies the postcondition.
Okay, thank you.
You're welcome.
Oh, there is maybe time for one short question, last question if there is. So let us thank the speaker again.
Thank you.